All right, so I'm going to go ahead and start going over 15 first. Please have your book bags off your desk, your problem sets out. I am going to take these up in a little while, so just keep it on your desk for me and have a calculator out. So we're going to use our calculators a lot today for some example problems, okay? And then somebody remind me I have to tell you something. Remind me later. Numero 15. Is that the one with the conjugate acid one?
Yeah.
Phosphoric acid? Okay. So if it says write the conjugate bases, so there's multiple conjugate bases of phosphoric acid. If this is phosphoric acid and it reacts, and a lot of times we're just reacting things with water because water can act as an acid or a base, and we can do a really good job of showing how it does that by adding an H or subtracting an H from it, right? So if this is an acid, the acid is going to be donating the H plus here to make what? So hydronium with a plus sign and H2, right? Because you lost a 2. So look over there. Yeah. So the H2, because there was an H that got transferred away, PO4 1 minus. Because once you've lost one of these H pluses, you lose an H, and you lose a plus sign. Well, when you lose a plus sign, you become a negative charge. So this is one of the conjugate bases. Okay. Now we're going to take this one. This can act as an acid. How do I know that itself can act as an acid? What's in the front? H plus, right? So we have H pluses there still to be had. So we're going to take this again, and we're going to go through it's called a second deprotonization. Okay, so the first deprotonization, what does deprotonization kind of sound like it's doing? So D, usually means kind of subtract or go away. And then protonization is like a proton, which is what the H plus is kind of considered. So the H2PO4 1 minus is going to do exactly the same thing as this one did. It's going to react with water, and it's going to donate an H plus over here. So then we again we'll make what? Hydronium. And now take away one H and one plus from that. It's not going to be H2PO4 1 minus, it's going to be HPO4 2 minus, right? Because as you lose another plus sign, you're running more into the negatives. And then last one, so this is our second conjugate base. This is conjugate base number 1, this is conjugate base number 2. It can do it one more time because it's a triprotic acid, right? Triprotic acids have 3 H's, so they can undergo this same process one more time. So HPO4 2 minus plus water. You guys tell me this time. Hydronium and, yes, phosphate this time because we've lost the final H because it got donated here, lost the final H, and we lost one more charge, so the charge went down to a 3 minus charge. Okay, so that's number 15. Tell me about number 12. Is that the weak acid one? My numbers are off from yours. Okay, tell me the log logic one? Log logic, number 12? Yeah? Okay. So log logic is a way of saying use your brain power of how logs work. Remember how log base 10 something is equal to that? That's how logs work in Algebra 2? Yeah? So if you ever have, for example, if you ever have like 1 times 10 to the negative third is equal to sorry, you're trying to find the pH of this. pH's function is negative log of the concentration of hydronium, right? So the negative log component is actually found in the exponent. So the negative log is equal to like this exponent here. So the negatives and negatives go away. So anytime you have a 1 and base 10 and you have an exponent present, that is the pH. So if you put in your calculator, negative log of 1.0 times 10 to the negative third, that would be the pH. So anytime I said, tell me the concentration of pH 3, pH equals 3 means your hydronium concentration is that. So just take your pH and put it as the exponent, or take the exponent and put it as the pH, whichever way you're going with it. So the hydronium is 1 times 10 to the negative third. What was the other one? Like 5 and 7, something like that. 6 and 10, close. Okay. So if it was pH 6, then you can see you're getting more basic, yeah? So then the concentration of hydronium is going to go down. That makes sense because you're actually going to write it as hydronium concentration is 1 times 10 to the negative 6, which is a lot lower than 10 to the negative third. It's like, 1,000 times smaller. So if we did it again, pH 10 is going to be even more basic. So our concentration is going to go way down. pH equal to 10. The concentration of hydronium is 1 times 10 to the negative 10th, which is an itty bitty number. And those are all in molar molarity concentrations. Any more on problems at 19A? 9A? BA? You good? Okay. Hold it extra desk for me and I'll come get them in a little bit. Let's do a couple introductions to reminders. Pull out reading guide 19 if you have it available. And I want you to tell me the difference between between equivalence point and endpoint. And then we're going to kind of talk about how that relates to titrations today. And we have a simulation that's kind of an eye-opener about what a titration is. Because we're doing a hardcore lab tomorrow, which is everybody's going to have in their hands $150 of equipment. Whew. Okay, so I want to make sure that you're highly qualified to do your lab tomorrow. So tell me, looking at your definitions, equivalence point versus endpoint. Go for it.
Equivalence point is moles of H plus equals moles of H minus.
Okay, this is the best definition ever. Okay, look how simple that is. The moles of the acid equals the moles of the base. And that makes sense. Equivalence point sounds like it's supposed to be equal. Okay, and then difference between that and endpoint?
Endpoint is just another indicator changes color.
Okay. Indicator changes color. All right. Can you thinking about your acids and bases? They're aqueous solutions, right? They're clear. You guys used some different solutions on Thursday and Friday. They're all clear. Can you really see the particles and see the moles in there? No. Okay. I naturally cannot just look at something and go, oh yeah, those moles and moles are equal. I think I'm at the equivalence point. You actually need pH paper or pH probe, which is a digital technology data collection thing. Or you need something else to help you see the results, see that they're equal. I cannot see that moles of H plus and moles of OH minus are equal, but I can use an indicator, a color change, to help me kind of see that it's going to be close to equal. So what we have to do is our job is to choose the best indicator for our particular reaction, because the indicator changing colors is trying to indicate to us, hey, moles and moles are equal right now, or close to it. So the equivalence point and the endpoint are not exactly the same thing. But if we choose a really, really, really good indicator that's really close to the point at which moles and moles are equal, the point at which the color change happens will be really close to the endpoint. To the equivalence point. So our goal is to make them really close, because we have to use the indicators. We're not like Superman, can't see the moles and moles equal. So we're going to see how those are going to be coming into play today. Okay, quick question or quick review. What's molarity units? Moles over liters. Okay, if I divided everything by 1,000, what would that prefix be in front of moles? Remember, if you have grams, if you move the decimal back 3 spaces, what is that unit? Or sorry, the other way. Move it this way. I'm going my way, looking at you. Kilos are bigger. Divide it by 1,000. Milli. Okay, so a meter and a centimeter and then a millimeter. You're going down, and prefixes and the units are getting smaller. So if I divided everything by 1,000, I would have something called millimoles over milliliters, right? So I'm going to start I'm going to use those a little bit today. They're exactly the same thing as moles over liters, because what happens if I cancel out the millis here and millis here? Millis and millis gone, moles over liters. The quantity is the same. It's just on a very, very, very small scale, because we don't use big liters of solutions. We use little bits, like milliliters of solutions. So it's something I just want to expose you to, because we're going to use that a little bit today. And if you're confused by it, always do moles over liters if you don't like millimoles over milliliters. Okay, so I drew this on your notes. It's got you give it an L-shaped graph and axes. And I'm going to talk to you a little bit about what titrations are before we start trying to talk about the differences between their molarities and liters and stuff like that, okay? So what is a titration? A titration is a volumetric analysis technique that helps to determine unknown molarity or volume. It depends on what the question's asking. But it's volumetric analysis. And all volumetric analysis means is that you're analyzing different volumes of an acid and a base. So it's like a procedure. And this procedure uses something called a burette. And the burette, oops, my marker is very off here. All right. The burette is a long, skinny piece of equipment. It's about this long. It's like this is 2 scale here. Okay, long, skinny pipette with lots of graduations on it, and the graduations are going to read opposite or upside down. It starts off down here at 50 milliliters, and it goes up here to 0 milliliters. So what you will do tomorrow is in your lab is you're going to fill up the burette to the 0 mark, and as you dispense liquid, you can measure exactly how much you dispense by, let's say you go from 0 down to here, and let's say that's like 15.20 milliliters, okay? That means that you dispense 15.20 milliliters into a beaker down here that you have something else in, like an acid or a base. This right here is, for us, is going to be filled with sodium hydroxide. And so it's called volumetric analysis because you're using this quantity of volume and you're using something else with it to calculate. So that's going to be a big piece of our experiment. And then I just told you you're starting with base in here. So what do you think you're starting with in a beaker down here? Acid. This is an acid-base reaction. And we're going to come to the point where we neutralize, right? Remember, acid bases, they neutralize each other. So we have an acid down here that we're starting with. If I measure the pH of this, what's it going to be about? Give me that guesstimate. pH of that acid. 5. It could be 5, it could be 4, it could be anything under 7, right? I'm going to go lower. I'm going to go like 2, just so I can start with a lower number. So on your axes here, label this pH and volume of base added. So if I'm starting off with a strong acid, and I'm adding base, what's slowly going to happen to the pH? It's going to start going up, right? But it goes up in this weird S-shaped curve, and I'll show you what it looks like. But we're going to start off with a pH of 2, because that's what I'm just assigning to my acid. It will depend upon the acid. And as I add base, it's going to go up. But it's going to go up kind of slowly at first, because they're starting to neutralize each other. And then all of a sudden it'll jump up like this, and then it will level out again. That's kind of what the curve looks like. It's kind of crazy, but that's how it looks. So I want you to label a couple pieces here. From this point, I'm going to kind of put a dash line here. From here to here, we have a lot more acid than we have base, right? And that makes sense because look at the pH. It's really low. So we have more acid than we have base. That's a greater than sign. More acid than base. So then tell me what's up over here. Right. More base than acid. And that's why the pH is so high there. Maybe it's up at here, let's call it, I don't know, 12. Let's say it's at pH 12 up there. So then we have this area in the middle where there's a huge jump. It's because there's so little acid, and you add one more drop. Add one more drop and it shoots up to pH of 7. Add one more drop after that, it shoots up to pH 10. Because there's very little acid in this region, and there's very little base actually too. And so then there's not very little base, there's very little more base than acid. So then it's going to shoot up really quickly in pH. So at the middle portion of the vertical, so the middle of the vertical is about here. Maybe that's a little high. Let's go like right there. Okay, that right there is the equivalence point. And at that equivalence point, that's where we say moles of H plus equals moles of OH minus. So that's a very important part of the puzzle. And for my example, I'm telling you that we have a strong acid, let's say HCl, reacting with sodium hydroxide, so that's a strong base. So what should their equivalence point be if they neutralize each other exactly? pH 7. That should be about pH 7. if I had a weak acid and weak base, I'm sorry, a weak acid and strong base. Let me draw this a second time down here. And right to the side, weak acid plus strong base. It's going to actually have this weird kind of feature to it, but I'm going to actually just show you the equivalence point. It's going to go up. See how it goes up faster? It goes up faster because it's a weak acid, so the base is really, really pulling the pH up very quickly. But its strong base is winning, so its equivalence point is not at 7. It's going to be at, like, I don't know, a 9, something higher than 7. So that's simply just because the strong base wins. That's gonna be the way I explain it. It runs the pH up faster because it's a weak acid and a strong base. So tell me what you think then if I did the same thing but with a strong acid weak base. Where would the equivalence point lie? 4 or 5, something lower than 7. Okay, so that one looks, what did I just say? Strong acid plus weak base. It's gonna stay lower longer, and then it's going to kind of go up like that. That's really bad, but that's kind of what it looks like. And the pH here for the equivalence point can be maybe a 5. Okay, so the pHs of the strengths of the acid and bases do control the pH of the equivalence point. All right, so at the equivalence, oops, sorry. If I can go back to where I was here. At this equivalence point, we have exactly the same numbers of moles of acid and moles of base. So if I had HCl plus NaOH here, what would it make? So I hear HOH and what? NaCl. If I have exactly the same moles of each of these, they were both the limiting reagent, right? They both point out exactly the same time. So it's the only thing left at that point. There's no reactants left, right? So there's all products made? Yeah? There's all products. There's no HCl and NaOH left over. It's only this. And Friday you guys did a lab on hydrolysis, and you said salt plus water yields some, acid and base parents. And you told me the pH that. So if you look at that, you know the pH is 7 because you know sodium chloride came from a strong acid and strong base. So I could easily give you that, and I could say, where would this pH lie? Acidic base for neutral, and that one's a neutral salt. So that's how you know it's a pH of 7. So a lot of these things are coming into the same picture now. But we need to bring in stoichiometry too, because like I said, it's a volumetric analysis, and we're calculating some things about molarities. So what I could do is I could say, okay guys, I'm telling you the volume of base you're using, I'm telling you it's 1.0 molar base. And I'm going to say, let's say there's 50 milliliters of acid in this container. The only thing we don't know is the molarity of the acid. So I'm asking for you to calculate the molarity of the acid. This kind of looks like M1V1 equals M2V2. And it sometimes can be true, but not all the time. So we're going to do it 2 different ways here. So a lot of the time, I will start you off with something called the standard. The standard is what's in the burette. I have this on your paper? Yeah, okay. So the standard is what is in the burette. And I'll tell you in the problem, there was 15.20 milliliters of sodium hydroxide added to the solution. And if I give you the what's in the burette, I'm always going to give you the molarity. I'm going to say always, very well, may not be always, usually given. So if I tell you the molarity and the volume, how are you going to get moles of the standard? How are you going to get moles of the standard? By your molarity and volume. Multiply them, thank you. Anytime you have both molarity and volume, multiply them to get moles. Remember that? Okay, that's moles of the standard, which in this case, in my first example, is a base. So then how do you get from moles of standard to moles of unknown? Well, if I tell you that the standard is the base and the unknown was the acid, well, that's just simply looking at the mole ratio between the BCE. Okay, so we're using mole ratios here again. And then I could actually get to moles, and then you can take moles to grams with the molar mass, or you can take moles to molarity. How do you get to molarity from moles? Divide by solution volume. Okay, liters in this case. So it depends on what we're looking for. But if I want you to get from moles to grams, you just use molar mass, or from moles and divide by the volume, you can get to molarity. I think this little picture is nice, but it makes a lot more sense in terms of a problem. Okay, so let's try this in a problem. I'm going to write down the steps for you. So the first thing you probably want to do is read the problem, underline the important pieces. So of this, what's important? Okay, here you 200 milliliters. Okay, but this is 200 milliliters of what? HBr. I'm going to write my stuff down on the side. You know me, I like to write my names down. So 20 milliliters of HBr, okay? What else? 20.05 milliliters of 0.1819 molar solution of sodium hydroxide. All right, so both of these pieces of information are regarding sodium hydroxide. And then the question says, what is the molarity of the HBr solution? You can, and I'm going to show you both ways. The M1V1 equals M2V2 is only a cheat. It's a way to do it for acid-base reaction that are 1-to-1 mole ratio. It will not work all the time. It will only work 85% of the time. So I'm going to show you both ways, but I want to show you the stoichiometry first and then M1V1. So the question is, what's the molarity of HBr? Okay, so always your first step should be to write the BCE out, because it is a reaction. If you have a reaction, you got to write it out. So the first thing you do is HBr plus sodium hydroxide. This is acid-base reaction. What's it make? So HOH and NaBr. Good, because so it's salt and water, and this salt is sodium bromide. And this is a, 1-1-1-1 all the way, so it's a 1-to-1 mole ratio. We can use M1V1 equals M2V2, but I'm going to show you the other way first. So the very first thing you want to do is find the moles of the standard. And the standard just simply means I know everything about the standard. It's also called the known. So the thing I knew everything about is sodium hydroxide. So I know the milliliters and the molarity, so I call that the standard or known. So let's find the moles of that first. So I'm just going to take, I'll go with millimoles and milliliters. I'm going to show you that one first. So the 20.05 milliliters times its molarity. And normally molarity I would write as moles over liters, but this time I'm going to write it as millimoles. So 0.1819 millimoles of NaOH over milliliters of solution. But notice the millis and millis, they're the same as me writing moles over liters. It's just the millis can cancel. I'm just not going to cancel them yet. The ratio is the same though. The number itself does not change. So milliliters and milliliters, you see they can cancel. So my question is not regarding sodium hydroxide, it's talking about the acid. So now I have to show a ratio from the base to the acid. Well, what's the ratio between these two? 1-to-1, right? So I'm going to put my millimoles or moles. If you choose to stick with liters, you just have to convert that to liters first. But millimoles of NaOH, there's one of them, and millimoles of HBr, there's one of them, just simply because the BCE says so. So my milliliters of solution canceled, my millimoles of sodium hydroxide canceled. What's my question again? Molarity, right? Molarity is just moles over liters or millimoles over milliliters. Right now I have millimoles. So what do I need to divide by? What's left that I've not used over there? The 20 milliliters, right? So how do I divide? I just, stop here, equals, and then divide. Or can I just multiply by the reciprocal? Like this. 1 over 20 milliliters. That's the same thing as dividing, right? We got that? Okay, just want to make sure our mathematics are sane here. I'm doing this right. So the only units left that don't cancel are millimoles of HBr over milliliters of solution. And if it makes you feel better and sleep at night, cancel out that milli and that milli, and you'll see now it's moles over liters, which is molarity. Okay? So then that's like, I don't know, let me get my notes here. You guys can practice calculating real fast for yourself. So you should do 20.05 times 0.1819, and then divide by 20, and you'll get 0.182 molar of HBr. So if you had done M1V1 equals M2V2, your problem would have come out exactly the same way. I'm just going to set that up real fast. The only reason you're allowed to do it here is because it's a 1-to-1 mole ratio. So you can use M1V1 equals M2V2. The molarity that's known is 0.1819 molar. The volume that's known is 20.05 milliliters. M2 is unknown, and the volume 2 is 20 milliliters because you have to keep this together and that together up there. So what would you have done to solve here? So times those like you did up here and divide by 20 like you did up here. So the mathematics are exactly the same. This is more correct because it's really showing the relationships between this reaction and how it works. So that's more advanced, and that's why I like to show you both ways. But you can solve for M2 this way and get the same answer. But sometimes you're not solving for molarity, and sometimes you're not solving for volume. What if you're solving for grams? That won't work. So you have to be comfortable with both ways. Okay, so let's do another one. And actually might be one from your lecture. Let's see here. So now I'll go over this one. Okay. Vinegar can be assayed. Who cares what that means? That just means checked, calculated. Determine its acetic acid content. Determine the molarity of acetic acid in a 15.00 milliliter sample of vinegar that requires 22.70 milliliters of a 0.550 molar solution of NaOH. So you guys tell me how to do it the stoichiometry way. Do what? Yay. Okay, so let's do this the reaction way first. And now vinegar is not a compound. So of the stuff it was talking about, what is the acid compound? I hear you. Acetic acid. What is the formula for acetic acid? HC2 3O2. Okay, that's awful. C2H3O2. Okay, plus who? Sodium hydroxide. Yields what? HOH. So we can see that this H here and this OH here got together, and then who else? How do I write this salt? Here comes first. This or this? Sodium, so sodium, and then acetate. So it's called sodium acetate. So plus NaC2H3O2. So we should be comfortable writing out equations, okay? All right, so we've got our BCE. Do you see any balancing needs? Is it balanced? Yeah, I see everything is balanced. There's one of everything of each of the four elements of ions. All right, so I'm going to do the same thing. I'm going to do it both ways. What do I start with? Okay, so 22.7. I'm going to actually go to liters for you this time so I can show you another way, okay? So how many liters is that? 0.02270 liters. So you bounce the decimal back 1, 2, 3, put a 0 there. All right, so that's how many liters of solution of sodium hydroxide. I'm going to multiply that by what? Thank you. It's really helpful when you guys help me out here. Moles of sodium hydroxide over 1 liter of solution. So I just took molarity and I broke it into the 2 units of moles over liters. That allows for me to have liters and liters to cancel. Now I've got moles of sodium hydroxide. Now what do? I don't care about sodium hydroxide. So I'm doing a 1-to-1 mole ratio, right? Because it's a 1 acetic acid for every 1 of sodium hydroxide. So 1 mole of NaOH for every 1 mole I'm going to put AA like that for acetic acid, just so I can have some space here. Okay, so I could stop here, calculate moles, and then get molarity, or I can multiply by the reciprocal again. Because I'm asking for determine the molarity, sorry, I never usually wrote that down. Determine the molarity of the acetic acid. So I've got moles, so I'm going to divide by, how much? 0.015? 0.015 liters. Only because we went to liters in the beginning, we got to stick with that the whole way. So it's up to you. If you like liters and moles, you go with this method. If you're okay with millimoles and milliliters, go with the first way I did it. Just basically, if you're going to liters, you have to backtrack and move your decimals back. The other one, you don't change anything. Nothing. It all cancels each other out in the end. So this will give us a number such as 0.809 molar acetic acid. And it would work out exactly the same way if you're doing M1V1 equals M2V2. It's just this is the part right here that sometimes is important. If it's not a 1-to-1 mole ratio, the M1V1 will not work. All right, I'm going to do a grams one, and I don't think it's on your lecture one, so I think it's on you practice, so I'm going to scroll to that in a second. Can I go forward? You guys are like, yes, kill me now, we're done. Okay, let's go. I'm going to do number 3 on this one for you. You guys have your practice ones in front of you too? Okay, I'm going to do number 3 here, because you'll see that this one right here says what's the molarity again, right? You'll see this one says what volume, so you're solving for V instead of M on that one. These are easier than number 3, so let me do number 3 for you. Oh, darn it, what did I do? It's stuck here. There it is. All right, so this is a little different. A 55 milligram sample of aluminum hydroxide, so let's kind of just give ourselves a second to absorb this. What is aluminum hydroxide? AlOH3, okay, has reacted with 0.2 molar hydrochloric acid. So we're given 2 pieces of information thus far. How many milliliters of the acid is needed? So question, volume in milliliters of the acid is needed to neutralize the aluminum hydroxide. All right, so we have very few numbers. 2 numbers, 1 unknown. What's the first thing you want to do? BC, let's get her done. So aluminum hydroxide reacts with hydrochloric acid to make what? So water, HOH, and 3. Aluminum chloride is AlCl3. Good. Balance it. 3 in the HCl, okay. And HOH, okay. And all right, so this is not a 1-to-1 mole ratio one. There's another one that's like a 1-to-2 mole ratio. Just be careful on those. So I know that I'm not going to do a 1v1. Like, and I'm solving for volume from grams and stuff. It doesn't fit. So the very first step we've been doing is to get to moles of the standard, right? We just did M times V to get moles. What other way could we get to moles from our given information? Huh? Say it out loud. Be proud. Come on. Grams to moles, right? Well, I've got milligrams. I can get to grams, and I can get to moles, right? And then I can do my mole ratio from the base to the acid, and then I can solve for volume. So let's start off by getting from grams to moles. So 55 milligrams of aluminum hydroxide. Get me out of milligrams. So 1 gram on top, 1,000 milligrams on bottom. All right, so now I'm in grams of aluminum hydroxide. All right, now can you give me some moles of aluminum hydroxide? What goes on top? I know, dude. 1 mole, good. So 1 mole of aluminum hydroxide weighs how much? Come on. have to look it up. Tell me what you're adding. So aluminum weighs like 26.98 plus 17 times 3. 17 times 3 is 40, huh? But this has an H as well. So I just added them. I just added that 16 plus 1. What is it? 51 plus 27. How much? 77.9, okay. So I'm just making sure we remember the 77.9 grams of aluminum hydroxide. All right, yay, success. We've made it to moles of the base. My question is not about base, it's about getting something related to the acid. So now what's my next step? Mole ratio. What is that mole ratio between aluminum hydroxide and HCl? 3 to 1, right? So who's going on top? HCl. So 3 moles of HCl, because there's a 3 here, over 1 mole of AlOH3. So, and then you kind of, sometimes it's nice to stop and make sure that everything is canceled. So milligrams have canceled, grams of aluminum hydroxide have canceled. Now moles of aluminum hydroxide have canceled, and now I'm in moles of HCl. I'm in moles of HCl, not, can I use a molarity to get to volume here? It's weird, but we can. What do I do? Anybody got me? Huh? If I multiply here, I am going to multiply by something. But if I multiply by molarity, right, I can't cancel. I mean, I can't, if I just put molarity, moles over liters, the moles don't cancel. So I flip molarity, right? So I'm putting moles on bottom. So this right here, which is 0.200 moles over liters, I'm just going to flip that ratio. So put liter on top, 1 liter of solution on top, and 0.200 moles of HCl on bottom. So now my moles of HCl and moles of HCl cancel, and I'm in a volume unit, which is liters. I'm going to stick with liters, and I can just, backtrack to milliliters here. What's up? Where at? Up here?
Oh.
That's molarity, and then I just I showed you how molarity expands out to the bigger unit of moles over liters. So 55 divided by 1,000 divided by 77.9 times 3 divided by 0.2. The total is 0.1057 liters. How many milliliters is that? Actually, I have milliliters here. I need one more zero. No, I don't. It's good. It's good. Huh? Because it should be 1, 2, 3. We move the decimal over to get to milliliters. Yeah. Oh no, I lied. I see what you're saying. So no, that's right. It's 10.57 milliliters. Is that right in liters? 10.57. Yeah, it's 10.57 milliliters. So that's how many liters is 0.01057. So milliliters would bounce the decimal back 1, 2, 3, which would give us 10.57 milliliters. That's the answer in milliliters. I'm thinking my decimals are in the right place here. Anybody? You checking me, Shania? You checking me? Huh? Yeah, I did. Oh, or to get from liters to milliliters, you divide by 1,000. No, sorry, multiply by 1,000. Sorry, because you're going like this: 0.01057 liters times 1,000 milliliters by 1 liter. Okay, perfect. So you guys have 3 more questions to do. The one I skipped, number 3, and then number 1 and 2 on yours. Do you see those? Okay, do one of those first, and I'll get you guys passed out laptops. The laptops are gonna on my website. There's a simulation on how to do a titration. It's a really cool simulation to walk you through how to, drop your base and put it in the acid and talk about the relationships between the ions and stuff like that. So you have to do this simulation before you can do the titration tomorrow. So I'll show you where that is on my website, but I do want you guys to work on your practice problems as well. If I can pull up my website real quickly, wrong page. It's underneath Unit 7. So underneath Unit 7, it says Chemistry Web Quest, Chemistry Acid-Base Titration Web Quest. The PDF or the Word document, either one will work, but it'll just take a second to get loaded. So it kind of starts you off with, give me a quick definition. You guys can do that really simply. And then the virtual titration, the link is there, allow, and it comes up like this. And it'll talk to you, okay? So you have to listen to your things and stuff. I prefer to work as your own person because you might be faster than someone else. You guys are responsible to get 50 minutes, get this done, and get your lecture notes done. If you have your lecture notes, okay? So just drop them out the box. If you didn't bring headphones, just spread out and listen quietly. It's just the person talks to you, so you don't want you to miss something. If you cannot rewind on it, there's no back button. You just like start over if you miss something. Sometimes these take forever to load up, so just get them loaded and get a problem on the way.